Hello, welcome back. This is the start of Unit 2. Go to Schoology. Unit 2, oh my gosh, I've got 2 units in Schoology now. Unit 2. As you'll see, I've got, you know, red A's, unit tests behind me, soon to have red B's. Those will be graded back to you just probably the next time I see you, will be the goal there. So, what are we doing? We're getting started into Unit 2. What are we doing here? Unit 2 is about describing location within a distribution. Where is a data point in a distribution? Unit 5, we're going to start talking about probability. Under today's folder, Wednesday, October 14th, there'll be another folder for next week's, and that'll be up Wednesday. You will see your learning objectives textbook homework, as always. Glossary. You don't need to worry about note cards this time. I'll say that again. Don't worry about note cards for chapter 2. Not that many words. If you want to make them, you're more than welcome to, but it's not as big a point of emphasis here. We're going to start doing math. There are formulas in there. If you want to write down the formulas, you're welcome to. Again, blank notes, completed notes. I'm going to have the completed notes uh, up here for the AP problems because I don't need to replicate if AP's done it already. I will talk through the stuff you see in blue. I'm going to work through it. If you just want to work through it, I don't care. I don't care if you don't want to watch the video and you just want to go through with the notes. But I'd watch the video because hearing somebody talk about it's useful. On that note, gosh, you can always schedule a Zoom call with me and we can talk about this stuff during the day, especially first block, plan block. If you've got something going on first block, you can Zoom. If you're not doing anything in your other class, you can Zoom conference me with me if you really want to. Send me an email. I don't care. So let's get into it. You see bookwork on there as well. Bookwork will be due the following Tuesday for you. So let's jump into it. Yeah, so here we go. Talking about chapter 2, modeling distributions of data. Talking about whole distributions, modeling distributions. The distribution we're going to talk about later on is going to be that normal distribution. We'll get there in 2.2 next time. So is what first vocabulary word? What is a percentile? And I'm going to give a definition that kind of has percentile in it, and you won't like it. The pth percentile is the data point below which p% of the data falls. You guys are used to looking at standardized test reports by now, probably. You get something in the mail, your mom does, somebody does, and says, ooh, you're in the 98th percentile of math. And you say, ooh, that's a big number. What's that mean? It means you've got a score better than 98% of your peers. And you say, why can't I be in the 100th percentile? Because you can't be better than yourself. You can't be better than everybody because you're in everybody. That's why you got like a 99 with a little asterisk if you're real smart. Okay, so we can calculate percentiles, and we can it's a proportion. P% of the data falls. We're calculating here proportions. The stem plot shows the number of wins for each of the 30 Major League Baseball teams in 2009. I need to update my notes. Find the percentiles for the Colorado Rockies, who won 92 games. Just look and say, okay, where's 92? That's right here. How many are the number less than 92 divided by the total times 100%? That's going to be, how many are less than 92? Well, if there's 30, you can count how many are 92 or better. 1, 2, 3, 4, 5, 6. There must be then 24 that are less than out of 30 times 100%. You knock that. Oh, we can use our calculator. 24 divide 30 times 100, and we can say, okay, that's a lot of glare. That's the 80th percentile. That is, the Colorado Rockies were better than 80% of teams. When are percentiles good? I don't love percentiles for the case of baseball teams. I like percentiles when, well, percent is per 100. If we're going to talk about percentiles, you should probably have at least 100 things, right? Otherwise, why not just talk about it as a fraction? I don't care. 16.6% of people, one of six people in a room. Just a just a thing that irritates a stats teacher. Okay, so I should probably change this, but I'm not going to. The New York Yankees, who won 103 games, you'll notice 103 is the largest number on there, so that's going to be the number less than 103. That'll be 29 out of 30 times 100% equals, well, it's not 100 percentile. 29 divided by 30 is times 100. We can call it we'll round and we'll call it the 97th percentile. So, notice you can't be the 100th percentile. The KC Royals and the Cleveland Indians, who both won 65, those are both right there. How many are strictly less than 65? Strictly less than 65, so that'd be number less than 65 divided by that total times 100%. 3 out of 30 times 100%. 3 out of 30, that's 1/10. That is the 10th percentile. And that percent sign ILE, perfectly fine with me. I will know what it means. AP will know what it means. You are good to use that abbreviation. So we can find percentiles, and we're asked down below to do some quick things with AP. Why don't you stop and ask yourself, can I do these? Can I ask some questions about crows? Crows have been eating some lead. What are they eating? Probably eating lead shot or something. I don't know. I don't know what these leads are doing. But take a look. Give yourself a moment to answer these questions about crows. Taking a look at the key. What does it say? 4 of the 23 crows had a lead level greater than 6. Therefore, the proportion that were classified as unhealthy, you had to look back and say unhealthy is greater than 6 parts per million. If you didn't underline that in the text, you should go back and underline it because we're always looking for those kind of threshold values. What's the percentile level of 17? 4 out of 23 is fine. If AP ever asks you for proportion, by the way, unreduced fraction, absolutely fine. What percentile is the lead level of 4.1? 5 or less than that out of 23 total. You got the 22nd percentile. So hopefully we're okay calculating those. Seems like a question AP or ACT might have asked you beforehand. The next page talks about cumulative relative frequency, and it gives a lot of examples. I want to just you work through this kind of on your own, but I'm going to talk about what the words cumulative relative frequency. Cumulative. You've seen that word before. What does this mean? Cumulative relative frequency. How much of the data is accounted for up to here? That's what cumulative relative frequency is talking about. Cumulative, accumulate, to build up. How much has built up? Relative frequency, well, how many times has it happened? Is frequency. Relative frequency is relative to the total population size. So cumulative is like how much has total buildup, accumulate. The counts, and relative is divided by your population size. Look at what the words mean. Statistics is nice because we can make up the words to describe what we're talking about. Cumulative, accumulate, how much is accounted for up till now, relative to the population size, how many counts. Cool. So we can find raw data. We can find cumulative frequencies. Cumulative frequencies say, okay, how many are accounted for up till 9? Okay, 3. How many accounted for up to 14? 3 and 6 makes 9. How many accounted for up till 19? 3, 6, and 8 make 17, etc. So we can find cumulative frequency by adding up totals. We can do cumulative relative frequency. How do we get from cumulative frequency to cumulative relative frequency? We divide by your totals. So we get cumulative frequency. How much is accounted for up to here? How much has built up? How much has accumulated? And then we make it relative by dividing by the total. say 3 divided by 30, 10% is accounted for up till here. 9 divided by 30, 30% is accounted for up till here, and etc. On the next page, we have a cumulative relative frequency about the distribution of median household incomes. Okay, so we've got median household incomes. What was the middle household income for the 50 states and the District of Columbia? So there's really, what, 51 data points here. And then we look and say, California with a median household income of 47,445 is at what percentile? So we know the median household income of California, and we're saying it's 57,445. That's right about there. And I draw a line up from 57,000, and I say, okay, what is the cumulative relative frequency? What percentile is it? How much is accounted for up till here? And then I take it kind of over, and I say, okay, looks like California is at about the 80th percentile. That is 80% of states have a median household income less than California. Cool. And then I can go back and ask myself, or a second question, kind of go in the other direction. What's the 25th percentile of this distribution, and what's another name for that value? Well, 25th percentile, we know the how much is accounted for up till here. So I go from 25, I take that out to about there. Take that down to there. Notice we went kind of backwards by the arrows this time. That looks to be at about $45,000. What do you call the 25th percentile? That's the first quartile. Cool. So we can talk about percentiles. And what are we doing? We're talking about where is a data point relative to everything else. And you've talked about percentiles before. Standardized tests are the most common places, but we talk about percentiles. What percent's greater than this? What percent's less than this? And that's a way of saying, where is this data point relative to everything else in the distribution? You can do this for like cars. You see those car apps or car ads on the television that says, "Ooh, you can find where your car price is in the distribution." You've seen these maybe. You can say, okay, 16% of people paid less than that. Well, 84% of people paid more than that. Maybe you're getting a good deal. So one way to talk about where a data point is with a percentile. The other way is with something called a z-score. This is another way to talk about where is a data point in a distribution. So the z-score, this is called the standardized value. This thing has a mean of 0 and a standard deviation of 1. And we say that z is x minus x bar over s of x. And sometimes we'll say it as x minus mu over sigma. You know, the value minus the mean divided by the standard deviation. What's the idea here? The z-score is saying, okay, here's our data point. We subtract the mean, we divide by the standard deviation. The z-score is the number of standard deviations above or below the mean. So this is another way to talk about where is a data point in a distribution. We can say here's its z-score. It's saying it's this many standard deviations above, it's this many standard deviations below. So this is another way to talk about where is something in the distribution. When is this always as useful? I don't know. Sometimes z-scores can be deceiving. Percentiles, less opportunity to be deceiving, but maybe they both have their place. Well, we'll talk more about when do we use percentiles, when do we use z-scores, when is one better than the other. So down below, standardizing and z-scores, we have here just another way to say what I've said up above. What does the z-score mean? All right, what does the sign, rather, of the z-score mean? Think about your time to finish a race. Use a different color here. Time to finish a race. Do you want a positive or negative z-score? Positive would be above the mean. Negative would be below the mean. Do we want a time that is above the average time or below the average time? Well, you want a negative z-score. Negative z-score means you're below the average. That means you're fast. You want to be faster. Score on a first statistics test. You want to be above the average score or below the average score? Above the average score, below the average score. Well, you want to be above average. You want a positive z-score. That is an above average score. So you need to consider the context. Right out to the side here, context matters. Always does in this class. You need to say, okay, think about what is it being above average a good thing? Is being below average a good thing? You need to be able to consider these things. So we can talk about what does z-score mean and what does its sign mean? So sometimes it's nice to make comparisons with z-scores, and I apologize for the block of text here presented to you, but welcome to what AP questions look like. Block of text that you got to dig through. Macy, we need a couple different colors here, is a 3-year-old female, is 100 centimeters tall. Great. Blue for boys, I guess. Needlessly gendered, r/needlessly gendered. Okay. Brody is a 12-year-old brother, 158 centimeters tall. Great. Obviously, Brody is taller than Macy. No duh. Okay. But who is taller, relatively speaking? Let's circle that phrase there, relatively speaking. A way to compare relative heights might be by using z scores. We can compare, you know, we might not be able to say, well, duh, but yeah, he's a 12-year-old boy. No kidding, he's taller. But is he? How does he compare to his cohort of 12-year-old boys? How does Macy compare to her cohort of 3-year-old girls? Great. According to CDC, the heights of the 3-year-old females is a mean of 94.5, standard deviation of 4. Mean height for 12-year-old males is 149 centimeters with a standard deviation of 9. So we can calculate each of their z-scores. We can calculate Macy's score. So z for Macy is, she's 100 centimeters tall. The mean height for girls her age is 94.5, a standard deviation of 4. So that's, what is that? 5.5 over 4. What is that? Get your calculator out. It's like 1.375? No. 5.5 over 4. Yeah, okay, I can still do math. That's good. Z-score of 1.375. Put a little. All right, and now we go ahead and do it for Brody. Z for Brody is he's 158 centimeters tall, mean height of 149, standard deviation of 9. What do we get for Brody? 9 over 9 equals 1. So what does this mean? So Macy is 1.375 standard deviations above the mean height for 3-year-old girls, whereas Brody is 1 standard deviation above the mean height for, what is he, a 12-year-old boy. So who's taller relatively? Macy is taller relatively. 1.375 standard deviations above the mean height. these next couple examples for you, take a moment, take 2 minutes. Make sure you can interpret what does a standard deviation mean, what a z-score means, number of standard deviations above and below. So take 2 minutes, try and work these next couple examples. We'll come back, look at the key. All right, turn over to the key. You can find Mark Grace's z-score. Oh, find his total. You got to go backwards. Calculate the number of home runs he hit going back and solving for X. You're going to get 15. 15 home run total is about half a standard deviation less than league average. In an AP example, what are you doing? You're solving for X. You're setting it up. What do you know? You know Z. You know the standard deviations, and you know the mean. You know those three from the box of data you're given. Go back and solve for X. I'm going to show the setup on that AP example. All right, going back to that AP example, setting up. It was kind of a weird one. You told standardized z-score negative 1.2. We have the mean and we have the standard deviation. What score did they receive? Well, z equals the value minus the mean over the standard deviation. So we know negative 1.2 equals the score minus the mean of 1045.7 over the standard deviation of 221.9. Once you've set that up, you can do just the littlest bit of algebra, arithmetic, to solve for that score. Hopefully we can do the algebra. Ask me in class if you can. Flipping on to density curves. What does a density curve tell us about? So what are these things? Density curves tell us about where's the value, what kind of values does this random variable take? And what are the most common, what are the least common? Where do we see the highest what is density? How much stuff is there per unit length, area, volume, etc.? How much stuff is there per unit of dimension, right? Great, that was useful, Mr. Kraviec. So, is it equally likely in all places? Is it a uniform distribution? We have these Bernoulli distributions, a yes or no, hypergeometric, binomial we'll look at later in the year. Exponential distribution, as values get higher, does the probability of taking those values decrease exponentially? We have the log normal, the normal distribution, which we'll look at in this class, the chi-square distribution, and the derivatives of the gamma and the beta distribution, which we will not touch with a very long stick in this class. Good God, we don't do any calculus in here, folks. So density curves, what do we know about these curves? These tell us about the density, how much of the data is in a region. These are density curves. They tell, okay, well, how much of the data? It's always on or above the horizontal axis. That is, probabilities of taking certain values are all, probability of some x is always greater than or equal to 0. And has area exactly 1 underneath it. Okay, well, what does that mean? If we integrated, oh no, if we integrated the probability density function with respect to x, it'd be equal 1. What does that mean? Just area 1 means that's all outcomes. So how would we say, oh, everything is probability 1? So if we integrate these functions down below over their domain, we're going to find that the area is always 1. All possible outcomes are represented by these density curves. And they say, okay, well, here is the highest density here. Here is the highest density here. Here are low densities out here. These say, oh, it's likely to be here. It's not likely to be here. The idea with these density curves is that areas under the curve represent probabilities of taking those values. So to find the probability that it takes a value between 2 and 3, to find the probability that some random variable takes a value between 2 and 3, that's the area under the curve between 2 and 3. And for you, the area is going to be a geometric shape that we can calculate with a rectangle area formula. How else would we do this? Calculus folks, we might find an integral. This is where we start. Ooh, integration. Okay. All right, mean and median of density curves. Median of a density curve is the equal area points. It divides the curve in half. The mean can be thought of the balance point. Mean is the center of mass. Folks who've taken physics, the mean can be thought of the center of mass. Where'd you put it to balance the sucker? Mean and median are the same for a symmetric curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail. So some things to highlight regarding mean and median. We've seen those before. So we are asked on the next page, using the following uniform density curve, what's the probability that the random variable has a value between 0.4 and 0.7? That is, that area. What's the probability that x takes a value between 0.4 and 0.7? Well, that's length times height. That's 0.7 minus 0.4 times a height of 0.125. 0.3 times 0.125. Where am I getting 0.3 from? That's the width right down here between 0.4 and 0.7. That's a width of 0.3, called a length there. 0.0375, answer there, D. Take a look at the notes if you need that slower. I feel like we can find the area of a rectangle. The idea here, folks, generally, is that areas under curves represent probabilities of taking those values. And we'll be talking about areas specifically under the normal distribution is what we'll be looking at. And we'll do a little bit of stuff with the chi-square later. We don't really talk about areas, but we kind of do. So as an AP example, talking about sales volumes, take a moment to do that one, or yeah, let's say take a moment to do that one. What is conveyed by the circle point? You've got an answer key. Take a moment, pause for 5 minutes. We'll come back and talk about the answer. All right, so looking at the key, in this context, the question, explain what information is conveyed by the circle point. 40% of sales agents sold less than or equal to $300,000. 40%, $300,000 in sales. What proportion between 70 and 80,000? Well, take a look at, 700,000 and 800,000. Take a look at 700,000. Let's draw ourselves a little line here. 700,000, about 70% of folks had sold less than 700,000. About 80% of folks have sold less than 800,000. 0.8 minus 0.7, 10%. What does it mean that it was flat? The percent didn't change as we went from 1 million to 1.1 million. Nobody was in that range. And what is the 80th percentile? We'll find the 80th percentile going back. We actually already found the 80th percentile right there. It is 800,000. So there we go. That is that one. Not too hard, actually. But they don't throw too many cumulative frequency graphs, cumulative relative frequency graphs at you on AP anymore. So last topic here in 2.1, and if this seems tacked on, it is. Sorry. What is the effect of adding or subtracting a constant? What happens to a distribution? What happens to a distribution when? Oh man, It's hard to write on that folded paper. What happens to a distribution when? Well, when we add or subtract a constant. Well, take a look. Here was your center. Now your center is over there. So we added C to that. Here was our original range. Well, now here's our new, it doesn't really look like our range changed all that much. Okay, so what happened here? The center, the new center had C added to it, but the shape and the spread were constant. When I add the same value to everything in a data set, the whole data set scoots over. Has the range changed? No. The small value had 10 added to it. The big value had 10 added to it. Everything is 10 bigger. Think if we had a scale, it was faulty. All the values measured on the scale were 10 pounds low. We had to go back, add 10 pounds to everything. Does the spread change? No. Center changes. Shape and the spread are constant. What happens when we multiply? The new center gets multiplied by C, and the spread gets multiplied by C, but again, the shape here is constant. Notice the center got bigger and the spread got bigger there. So both are affected when we multiply. So when we add, it's only the center. When we multiply, it's center and spread that are affected. So that's all I got for you. Good luck on the homework. We'll see you in class.